Hello again, physics friends. We are back and we're going to talk about Stern-Gerlach interferometers. Now, this is simply an extension of the idea of a color or hardness interferometer, but now applied to Stern-Gerlach apparatuses. Before we talk about interferometers, though, let's just refresh what we know about the analyzers, right? So a Stern-Gerlach analyzer, like what's drawn here, did something similar to a color or a hardness box, right? It created a correlation between the attribute of an atom. In this case, remember that these Stern-Gerlach analyzer oriented in the z direction is making a measurement of the quantity mz, which is the magnetic alignment of the atom in the z direction. And there's two possible outcomes here for that measurement. It's a two-state system. Either the silver atom is aligned so that it has mz plus, or it has mz minus. Now this mb term, remember, is a constant. We can basically think of this as mz plus 1 and mz minus 1. Okay, so a Stern-Gerlach analyzer correlates the value of mz with a position, either the upper or the lower track. Okay, and that's similar to what a color or a hardness box did. It correlated color or hardness with a particular location. Now remember that when we put a hardness box, when we built an interferometer out of a hardness box, we found some new information. And we uncovered some new facts about the quantum world. So in particular, if we took the hardness box with one input and two outputs, we had the hard output and the soft output. And if we then use mirrors to redirect these atoms and a merger box to merge these atoms, now we have a Stern-Gerlach interferometer. And the key idea here was that although the hardness box used to sort atoms spatially by their properties, these mirrors and hardness boxes re-scramble the spatial information so that hardness is uncorrelated with position anymore. So when you look at the output of the interferometer, you just see an atom or an electron, and you don't know which path was taken. And because you don't have which way path, the electron exists in a superposition of having taken both paths. Okay. So we're going to introduce an analogous device for silver atoms, and we'll call it a Stern-Gerlach interferometer instead of a Stern-Gerlach analyzer. And since we're basically from here on out only going to be talking about this kind of interferometer, we'll just call it an interferometer rather than a Stern-Gerlach interferometer. Or maybe we'll call it an SGI for a Stern-Gerlach interferometer. Okay, so what does this consist of? Well, similar to the hardness interferometer, we start with a hardness box. In this case, we'll start with a Stern-Gerlach analyzer, right? So the analyzer has a given direction, and we're piping the atoms that are deflected by that magnetic field so that they end up moving horizontally. And we're going to stack onto that, or tack onto that, a merger box, or we might call it a recombiner. Okay. So we start here with a Stern-Gerlach analyzer, and then we're going to have a recombiner. The recombiner basically takes those two paths and makes it one again. So it's almost like a little wishbone shaped thing. And out you go. So we might call this the recombiner. And that's kind of playing the role of the mirrors and the merger box. And together, this whole device, we're going to call the Stern-Gerlach interferometer. And notice the difference here. A Stern-Gerlach analyzer has one input and two outputs. A Stern-Gerlach interferometer has one input and one output, just like the hardness interferometer did, one in, one out. I don't really want to draw this elaborate shape every single time, so we're going to have a slightly more simplified version, and it will look like the following. We'll have our box, which is the analyzer portion, and we'll label the branches A and B because we have two pathways through this device, and then we'll put a second box here, which is the recombiner, but we'll just remember that it's doing the recombining. We won't actually put a label on it. And you might ask, well, why bother drawing two boxes? And two reasons for that. Number one, because a single box we know is an analyzer, so a double box is an interferometer. And number two, we're going to have this space in here between the analyzer portion and the recombiner portion where we can insert a piece of paper or a piece of metal or an absorber of some sort that will block one path. Okay, so that allows us to kind of inject a blocking device. If we do inject a blocking device, then any atom that would have taken that port would be absorbed and lost to our system. So you can think of it as a way to remove atoms from the system. The other thing that blocking a path does is it forces the atoms to take the other path if they're going to get out. So for example, if we block the upper path here, so I'm inserting my little card or my blocker. I'm now blocking the upper path. That means all of the atoms, in order to get to the output, the atoms must have taken path B. Well, if they must have taken path B, then they have the property of the atom that took that path when they exit. So for example, this is a Stern-Gerlach analyzer in the Z direction. Right? So the B port is like the minus port. And so an atom that makes it out of this device with A blocked means that if path B was taken, then the atom has Mz equals minus Mb, the minus value for a measurement in the Z direction. If we didn't block path A, then we can only say that the atom was in a superposition of having taken both paths, and therefore it's not a measurement of Z, but instead the state of the atom is unchanged. So whatever the input state is, that would be the same as the output state. Okay, so we've introduced the idea of an interferometer, and now we're going to make use of it and see what we learn about the quantum world through these devices. So what we have here, this is going to be our apparatus for several experiments. And in each of the experiments, we're going to block a path or not block a path. So we have a Stern-Gerlach interferometer that's oriented in the X direction, okay? So this is, I would call this an SGI sub X, or an interferometer with an X orientation. Following that, we have an SGA-Z, a Stern-Gerlach analyzer oriented in the Z direction. We're going to input atoms into the interferometer, and all of the atoms are going to have a defined Z orientation, which is positive, meaning aligned with the plus Z direction. So you can imagine that these atoms may have just come out of an SGA-Z themselves, out of the plus port. Okay, so we're going to have a few experiments here. So experiment, the first one, we'll call it experiment 9.1, is that we're going to block branch A. Okay, so branch A is blocked. So here we go. We have branch A now blocked visually. We're inputting Mz plus. In order to make it to the intermediate state, the atoms must take branch B. Is there a chance that they will take branch B? Well, yes, because when you go, if you send in an atom with Mz plus into an X analyzer, you have a 50-50 chance of taking each path. So half the atoms are going to get blocked by this barrier, but half the atoms are going to make it through to the intermediate position. When they make it through to the intermediate position, the atoms are going to have a defined X orientation, and the value of that parameter will be minus MB because it took branch little b, which is the minus branch, right? So if we were to label these branches, we'd have a minus and a plus branch in the X direction. Okay. But we've already lost 50% of our atoms. Okay. And now we have an atom with an X orientation of the minus direction. We put it into a Z analyzer and we look at the output, which is the minus output port. Well, we know that an atom with an X orientation has a 50-50 probability when sent into a Z port. So here we're going to have atoms coming out in the output. They will have mz equal to minus mb, but we're going to lose another 50% of our atoms. So for example, if we started with 100 atoms at the input, then we would have 50 atoms at the intermediate, and we'll only have 25 atoms at the output. So the overall probability for input to output, the probability of transmission, is only 25%. Okay, well, moving on to the next experiment, 9.2, we're going to have exactly the same setup as 9.1, except instead of blocking branch A, we're going to block branch B, and we're going to have the same transmission probability, right? Because we're still going to lose 50% of the atoms in going from input to intermediate. The difference, though, is that the atoms that make it through will have taken the plus port, or the plus path, and because they took the plus path, they now have a defined x orientation of plus mb when they reach the intermediate state. But an atom that is mx plus still has a 50-50 probability of making it through the Z analyzer, and so we're going to lose another 50% at the output, and at the output, the state is mz minus mb, as before. So if we had, say, 100 atoms at the input, we would have 50 at the intermediate, and we'd still have 25 at the output. So the in to out probability of transmission is still 25%. So here's where things get interesting. In experiment 9.3, we do not block either branch, so we leave the interferometer open. Okay, now classically we would say, okay, an atom has come in, it has two possibilities. It's either going to take branch A or it's going to take branch B. If it takes branch A, it will end up at the intermediate state with mx plus, and then it will have a 50-50 probability to make it to the output. If it takes branch B, it will make it to the intermediate state mx minus, and therefore it will also have a 50-50 probability of making it to the output. So the classical prediction, which turns out not to match experiment, the classical prediction is that you get 50% transmission at the output, meaning to go from in to out, you lose half of your atoms, and they're all lost in the Z analyzer. 100% make it through the X interferometer. But when you do this experiment, the actual result is that you get no atoms at the output. So the actual result is that you get no atoms at the output. If you get no atoms at the output, that means that the intermediate state must have been 100% Z plus, because all of those atoms would get blocked. How is it possible that you have a defined Z state here, mz equals plus mb? How is it possible that you have a defined Z state here if the atoms have gone through an X interferometer? Well, notice that the intermediate state is exactly the same as the input state. And the reason for that is that an interferometer that is unblocked and unwatched makes no measurement. Okay, so we can say that an interferometer that is unblocked and unwatched, meaning that we don't monitor the paths that are taken, makes no measurement. Okay, and as a result, the state doesn't change. So the atom state after the interferometer equals the atom state before the interferometer. In other words, in this experiment, the input state is the same as the intermediate state. And indeed, that's what we see experimentally. Okay, so here we know that we're going to get 0% transmission. Because all of the atoms at the intermediate state are Mz plus. Okay. Now notice this is this result has the hallmark characteristic of interference, because if we have no blockage, we get 0% transmission. And yet we saw that if we block port A, we get 25% transmission. And if we block port B, same result. So if you add blockage and you increase the transmission, that is a kind of signature of wave-like interference, like we saw with the two-slit experiment. And so somehow we can think of this as atom interference, where the exit probabilities are enhanced by blocking one path or another. Loosely speaking, we can also think of an unblocked and unwatched interferometer as a do-nothing device, because it does not change the state of this atom. The magnetic alignment before and after are the same. So this result would be exactly the same if we just erased the interferometer. In that case, we would still have no atoms making it through, because we'd be sending Mz plus into an SGAZ, and all of the plus atoms are ignored. None of them come out of the minus port. So in summary, if we do not have which-way information, then the atom state is not changed when it goes through the interferometer. If we do have which-way information, in other words, if we know that the atom took path B, then the atom at the exit adopts the state of the unblocked path, or the state of the path that it took. So it turns out that we don't have to block a path in order to tell which path was taken. We can just watch a path, or watch both paths. So what we have here is a similar experiment, we'll call it experiment 9.4, where we're not blocking, but we're just watching for atoms. And here we're watching using a bright light source, so we can call this our light source. And as an atom goes through this interferometer, if it takes branch A, we'll see a little reflection of light, a glint of light, if you will, because the light from this light source would interact and bounce off of the atom and come to our eye, and we'll be able to say, aha, the atom took path A. Okay. Or it took path B, either because we have a light source over there, or if we don't see a glint of light, then that means it didn't take path A, it must have taken path B. Okay. Now, if we don't have that light source, then we have 0% transmission to the output. But when we do have this light source, all of a sudden our output transmission goes up to 50%. So if we see glints of light, using our light source, then we have which-way path information. And if we have which-way path information, then the state of the atom here in the intermediate position is not Mz plus. It's either going to be Mz plus, Mx plus, or it's going to be Mx minus, depending which path we saw the light on, okay? And since all of the atoms are going to make it from input to intermediate, we have 100% of our atoms here. So if we put in 100 atoms, we still have 100 atoms. Now we can see that we are going to get a lot of atoms at the output, because if the atom is Mx plus, then it has a 50% probability to make it to the output, and same if it's Mx minus. So overall, we're going to see a 50% transmission at the output. So we have 50% transmission. If you have, or if you know, which way information. So that's interesting. We don't need to block the interferometer. We can leave it open, but we just need to have knowledge of which path was taken. And when we do that, we change the output transmission probability from 0% to 50%. Now we could put a light source, at both of these ports. Put a light source at port A and port B, and then if we see a glint at A, the atom took path A. If we see a glint at B, the atom took path B, and that's fine. We could also get rid of the light source at B, for example. But we would still have the same result, because if we saw a glint of light, we would know that the atom took path A, and if we did not see a glint of light, we could infer that the atom took path B. So with two slits, you only need one light source to determine which path was taken, and the output probability will stay at 50% even if you have only one light source. Now you might think, I wonder if the interaction of this photon with the atom perturbs the system in such a way that it destroys the interference phenomena or destroys the wave-like phenomena. But the amazing thing is, you can show that if you get which way path information using this light source, you can subsequently re-scramble that information to lose information about which path was taken. And in that case, you recover the interference or the wave-like effect. In other words, you can erase the which way path information even after you knew it. So you don't irrevocably alter the nature of this atom by hitting it with a photon. You can still re-scramble the which way path information after this point and still recover the original result that no atoms will make it through. This phenomenon is described in more detail in the quantum eraser experiment. I encourage you guys to take a look at that. It's really fascinating. So we've come to a nice stopping point here. We see that we have this new tool, the Stern-Gerlach Interferometer, and we know that if the interferometer is unblocked and unwatched, then the atom enters and exits the interferometer in the same state. No measurement of a magnetic orientation has been made. But if we block one port or the other, or we monitor one port, the other, or both, then we know the state information of the atom at the exit of the interferometer is either going to be the state of the path that it took. So then we are making a measurement of the magnetic alignment in the direction of the SGI. So we now have a really interesting set of tools here. We have a Stern-Gerlach analyzer that we can orient in any direction, and we have a Stern-Gerlach interferometer, which we also can orient in any direction, z, x, or any arbitrary angle theta. And we'll continue our exploration of the quantum world using these tools in subsequent videos. Take care and be well.